Okay, so for our Indie Lab, we did it on noodles. Okay.
Okay, so the purpose of this lab was to explore and understand the temperature rate of change for mac and cheese noodles. And we used various quantities of bags to insulate the noodles, and we are testing Star Wars Kraft mac and cheese noodles. And we predict that as more bags are placed around the noodles in a temperature-controlled environment, the temperature rate of change will decrease due to insulation.
So this is some of the equipment that we used. Temperature sensors, temperature-controlled environment, which is my fridge. We set that to 42 degrees Fahrenheit, which is like 6.4 degrees Celsius or something like that. And then we had a gas stove, pot, and all the ingredients that went into making the mac and cheese.
Okay, and so this is the procedure. And so basically you go to your closest supermarket, buy all the ingredients, and when no one is looking, you just take 25 bags from the self-checkout area. Then you go home really quickly. When you get home, boil a pot of water and then put the noodles in and like make sure you like count out.
90 noodles. Or have a leaving balance to max your noodles, but we just counted out 90 noodles each time. There's about 180 per package, so we split the package in half. And then set your laptop on top of your fridge and check the temperature sensors to make sure that they're working, and adjust your data collection time to 1800 seconds for 30 minutes, because I didn't do that 3 times, and so I wasted like 2 hours of data collection that I could have done. So make sure that you do that. And then prepare your ingredients while your noodles are boiling, and then drain your noodles, and then put your mixture in. So the noodles in your cheese mixture, and then put them on a bowl, and you're going to keep this bowl constant throughout the entire lab. And then you're going to put that bowl of noodles into your bag mass, which is going to be like 5 bags or 10 bags, whatever step you're on right now. And then you're going to put your temperature sensor in the middle, close the fridge, and then collect your data.
And then this is the diagram, and then just some various things needed.
Yeah.
And so our background basically was Newton's law of cooling, which basically is this this temperature at the time that it was.
Any time that you choose would be the ambient temperature added to. Ambient temperature is the temperature of the thing that it's cooling in.
So
in
the
our
fridge.
Yeah, our fridge. So it'd be the initial temperature minus the ambient temperature times e to the negative kt, and k is a constant, which is what we moved the equation around to solve for with our actual data points. So there's that. And the rate of change of the temperature of the object is basically proportional to the difference of its own temperature in the ambient.
So this is just our data with like the initial temperatures, which we found was really hard to keep constant because of like the interchanging that took place when you like moved the bags, like, and then you like put it in the bags, and then like the temperature sensor possibly could have moved there. And then this is our average K value for each, which we found really didn't fluctuate in the way that we kind of hypothesized, which we think is due to the fact that there had to be an opening in the bags for us to put the temperature sensors inside.
We found that we decided that if we would have had Bluetooth temperature sensors that could have synced data to our laptop, that would have been like a better way, because then we could have closed off the bag and not have had to have like this hole to stick our temperature sensor in and everything. And obviously, since we didn't keep the initial temperature the same, that factored into our equation, so that caused some error. But overall, it went from like 0.03 to 0.02 down to 0, which was our Yeti tumbler, which is a cup that uses a vacuum seal around the outside, so it's supposed to be an ideal insulator. Obviously, those don't exist in the world, but it kept it to where its constant was close enough to 0 that we could call it 0, because it was like 0.00000, and it just kept going. And that means that, we'll talk about that later. Okay, sorry.
And so this is like basically what our data looked like for most every test we took. This would be the initial temperature, and then it was like a decrease, like a kind of thing. Yep. And then it's temperature in degrees Celsius first time. Yes.
So our K average versus number of bags, we were hoping to see like
this.
Yeah.
But it kind of goes from somewhere down there, makes it to the end.
Yeah. So it makes it to 0.
Yeah.
Yeah. So this is our whole mathematical analysis. So basically, it just tells you how we got the equation, which we really had to like look this up and research how to find it. We found a great website which really helped explain it. So it just tells you how you derive to get the equation that's over there, which was the one that we talked about earlier. And then this is what we took to find all of our constants. So we had 7 graphs in total, I believe. And we used this equation 10 times per graph to get an average K. So we found 10 constants out of each graph and then average them to get our like average constant. So you take the natural log of the initial temperature minus the ambient temperature divided by the temperature at whatever time point you choose minus the ambient temperature, and then all of that divided by time is how you get your constant.
And so obviously one major source of error was that the bags were slightly open in the refrigerator, which we think definitely contributed to the constant that we received. And then the initial temperature was not the same for each trial.
And obviously like initial temperature factored into the equation. So it was hard to get the same initial temperature, but we could have like waited a little bit longer, I assume, until they all cooled down to around the same.
And then sometimes, like once Emily's parents accidentally opened the fridge.
For like half a second.
Yeah.
They're like, they come up to me and they're like, oh, we accidentally opened the fridge. I was like, I told you no, not for 30 minutes. But they shut it as quickly as possible. So we lost a little bit of our ambient temperature, but okay, sorry.
And then the temperature sensors could have moved inside the bag.
So basically we got a constant K value from our calculations, which is good since K should be the same for each equation. So like in the equations they were about the same, but then they should have decreased throughout like the adage of bags, but it didn't differ like we believed it would. We found Newton's law of cooling, which ultimately allowed us to find an average constant for each graph that we could plug in to create a rate of change equation for each graph we had. By understanding the relationship of the value of the constant to the amount of insulin provided, we can now like conclude that the smaller the constant is, the better the insulator is. And we know this because like the Yeti, which is an almost perfect insulator, had a constant of 0. And it makes sense because the rate of change equation K, the constant is an exponent. So if the exponent is 0, then the product is 1, or what, like it turns the number into 1, and 1 multiplied by anything is the same number. So when you derive that, it would be, your equation would be, get you down to your initial temperature is equal to your temperature at any time. So this equation says that in a perfect insulator, K would be 0, because no matter how much time passes, the temperature at that time would be equal to its initial temperature, therefore the temperature never changes. So by acknowledging that a constant of 0 represents a perfect insulator, we can determine that the closer to 0 K is, the better the insulator is, because the temperature change will be less.
The end.
That's under 8 minutes. Good. We have time for one question from the audience.
Okay.
How can you be sure that like the hole in the bag was such a huge error, and it wasn't just that the plastic was really an awful insulator and didn't cause a lot of change?
I mean, we couldn't like really say, but obviously if there's this giant hole, because it was like the opening of the bag hole, then obviously a lot of cold is seeping in, or a lot of heat is going to be able to get out, rather than like staying in like a tight, no air thing. Yeah.
Oh, I'm sorry, Jack. We don't have more time.
Oh, whoops.
No, that's fine. That's fine. I'm glad that you want to ask more questions. You can ask them afterwards. You could have like put something on it to close the bags.
Yeah.
Next time would do such a thing. Okay. Another thought that I had was you defined those Ks with only one significant figure. Would it have been better to take out 2 so that we could see, not such staccato graphs? And maybe there's more meaning in it.
Possible. They were all about the same though. They all rounded off to like, they were like 2 point like. What,
Yeah, if we would have done that, that changed the significant figures, so they would have been off by like values of like 0.000, like 5 at the most.
Yeah. There was very slight differences, so that's why we just rounded it to 1.
Cool. Thanks again.
Thank you.